Now I'm going to talk about data types. I've re-recorded the next few minutes because I wanted to change an example that I used before to a newer, clearer one. The code file currently on my website as of May 18th, 2020 is the one that I'm showing here. You don't have to become an expert on all of the types of R objects, but it's important to know a little bit about the major types of objects in R because this information will help you figure out what is going on when you get errors or your code has unexpected results. Is this variable or object really what I think it is? Should be one of the first questions you ask yourself when something goes wrong. So, as I've mentioned before, vectors contain items of the same type. So, the vector x, which I created earlier in this session of the workshop, contains all numbers. It's a numeric vector. The vector race, which is contained within the data frame that I read in earlier in this workshop session, is a factor. It contains elements, all of which correspond to labels of the levels of the factor. And finally, if I print to the console the result of converting race to a character, um, then I will get a vector, all elements of which are character strings, such as Asian, black, and white, which in this case are not labels of a factor any longer. They're just literal strings starting with, for example, a capital A and then a lowercase s, and so forth. Notice that if I attempt to create a vector by concatenating elements that are not the same type, R will attempt to coerce them to the same type. So in this case, I tried to concatenate the number 1 and the character A, and the result was a vector of two elements, the first of which is the string of the numeral 1, followed by the string of the character A. So that 1 is not the number 1 anymore, but it's in a sense the letter 1. Um, it's useful to know about functions that convert between data types. I alluded to one a second ago when I converted race, which was a factor in the data frame, to a character vector. But here are some simple examples demonstrating what those functions can do. So as.numeric will um, will attempt to convert something to a numeric variable or vector. In this case, I'm providing as input the string of the numeral 1, and the as.numeric function successfully converts it to the actual number 1 as it should. Then the opposite is also possible, as dot character of the number 1 will convert it back to the string representing the character 1. Obviously, these functions are not especially useful for um, individual data elements like the string 1 or the number 1, but they're very useful for vectors. They work element-wise on vectors. And so if I had an entire vector of strings that were supposed to be represented as actual numbers instead, then it might be convenient to be able to convert them all to numbers simultaneously. If I call as.numeric with the argument um, the letter A, I'm going to get two things. First of all, the output of that function is a vector of length 1, just like the input, just the letter A. Um, but it's a missing value because there's no numeric version of A. So this is appropriate behavior for when it was unable to coerce the letter A to a numeric type of data. But I also get a warning message at the console that there were missing values introduced by coercion. Um, this may seem obvious in the example that I just showed you, but if I had, as part of a longer bit of code, attempted to convert a vector of 1,000 elements to numeric, and 999 of those were valid numbers, simply encoded as text, and one of them was the letter A, then I might appreciate the heads up that one of my elements, at least one of them, was converted to a missing value through the attempt to coerce it to a numeric data type. This might come up in real applications. For example, if I had participants type in their age as part of a survey, and then I converted the resulting string to a numeric format. Perhaps the vast majority of participants typed something that could be easily converted to a number, but maybe a few just mashed their keyboards or were bots attempting to guess what the correct answer to the question was. And so I might actually want those nonsense responses to be converted to missing values. But if I didn't know that they were there, it might be useful to see a warning message that tells me that that happened. And here's an illustration of how it works when I plug a vector into the as.character conversion function. So here I've concatenated 1, 2, and 3 into a vector and plugged that in as the first argument, the only argument to as.character, and it converts each element to a character as it should. Vectors contain elements all of the same type. They're required to. That's why when you attempt to concatenate different types of things into a single vector, it are attempts to coerce them to the same type. Lists, on the other hand, are a different type of R object, and they can contain different data types. So if I run this line of code, it attempts to create a list where the first element is the letter A and the second element is the number 2, and it works fine. This list has the first element, the letter A, and the second element, the number 2. There's not a constraint that elements of lists have to be the same type. In fact, lists can even contain elements of more complex types, such as vectors. So this list was created with two arguments. The first was the full string, this is a list, and the second of which was the result of concatenating the numbers 1, 2, 3, and 4 into a length 4 vector. And the result is a single list object, the first element of which is that string, and the second element of which is just the vector 1, 2, 3, 4, a length 4 vector. So lists are ways of grouping together any number of more complex data types into a single object that you might want to refer to by name. To retrieve individual elements of lists, you'll want to use double brackets most of the time. So to illustrate that, I'm going to create a test list that's the same as the list I just printed to the console. A list with two items, two elements, the first of which is a long string, and the second of which is a length 4 vector, and that's called test list. To illustrate, I'll print test list to the console. It's the same. If I want to retrieve the second list item, I'm going to uh, I'm going to run the line of code test list double bracket 2 close double bracket. That results in just the length 4 vector that is the second element of test list. Then I can perform normal vector operations on that vector. So for example, if I wanted to retrieve the third item of the vector that is the second element of test list, then I might run a line of code like this one, where the first portion of the line of code retrieves the vector that is the second element of test list. And then, just like we're always allowed to do, I use single square brackets to subset from that vector. So I'm going to retrieve the third element of that vector. It might appear confusing that that square bracket 3 close square bracket immediately follows the double square brackets that retrieved the vector from the list, but you can think of it as two chunks of the line of code. This one specifies a particular vector, and this one does what we normally do to subset from vectors. And there, of course, the third element of that vector is the number 3. It's useful to know about the double square brackets to retrieve specific list elements because many types of statistical output are actually lists, and sometimes you want to mess around with particular parts of the result of a statistical function. To illustrate, I'm going to store the summary of a regression model as a new object called test. So here I'm fitting a regression model with the formula score tilde gender asterisk race asterisk age, which we've done above. This will fit a regression model with a three-way interaction between gender, race, and age, predicting score, and it will include all of the necessary lower order terms to make that three-way interaction sensible. And then it will retrieve the summary of that regression model and store it in the variable test. There's that summary. You might want to retrieve the standard error for the age term, this value right here, 0.139966. You could just type 0.139966 for whatever operation you want to do. But if you wanted to do this repeatedly, or you wanted that that number in a more precise format, then you might want to write code that explicitly retrieves that element of this table. Um, the most intuitive way you might attempt to do that is by calling the name of the summary object and attempting to use square brackets to retrieve the fifth row, second column, which this appears to be. But that doesn't work. I get an error message when I try to do that. And that's because test is not just this table. It's actually a list with more stuff in it besides that table. And so I get this um, confusing error message that tells me that there's the incorrect number of dimensions. But the error message makes sense if you realize that R doesn't think of test as just being that table that you were thinking of retrieving elements from. So one way to see what elements are in test is to call names of test. This will tell me the names of some of the elements contained within test. And one of them is called coefficients. That is the name of the table that I actually want. So if I call test $ coefficients, then I get just that table. And it's a matrix, and I can easily retrieve um, elements of that matrix using square brackets. So here, test $coefficients square bracket 5 comma 2 does retrieve the standard error for the age term. I've referred to the coefficients element of test by name using the $, just like we do to retrieve variables from data frames. Remember, data frames are just lists of vectors. In this case, the list contains some things that are not just vectors, but that's okay. I can still use the $ to retrieve a named element of the test list. But of course, I can use the double square brackets as well. Coefficients is the fourth element of test. You can see that here. It's listed fourth in names of test. And so the fourth element of test is that table, the same table that can be referred to as test $coefficients. And within the fourth element, I can retrieve row 5, column 2, just as I did above. It can be helpful to know about the class function that will tell you information about what class an object has. If, for example, you get an unexpected error message and you suspect it might be because the thing you're referring to, the object you're referring to, is not the type you expect it to be. So I will call class of test as one illustration. This object is a summary.lm object. The information there is stored like a list, but it's a special type of object that was created just to be able to display nice summaries of regression models. If I ask for the class of a vector constructed on the fly by concatenating the elements 1, 2, and 3, then it will tell me it's a numeric vector. Numeric is its class. Similarly, if I ask for the class of a string vector constructed on the fly, a character vector, then it will tell me that it's a character vector. If I ask for the class of a list that contains string elements, it will tell me it's a list. If I ask for the class of a data frame, empty cars, remember, was an example data frame that we've worked with a little bit before. If I ask for the class of that data frame, it will tell me data frame. And if I ask for the class of a specific column of that data frame, it will again tell me numeric because the MPG column is a numeric vector. Also, type of is another function that gives you information about the type of an object. Most of the time, class will answer the question you're trying to get answered more readily, but type of empty cars helps me illustrate that empty cars is a type of list. As a data frame object, it is a type of list. This is also a way to illustrate that the regression summary table that was referred to as a summary.lm object when I called the class function. If I call the type of function, I can see that that's also a type of list.